nanohub.org.
Online simulation, and more for nanotechnology.
So welcome back to the second part of the MAST-ML series. Next, we're going to be discussing the Materials Simulation Toolkit for Machine Learning, MAST-ML, automating development and evaluation of machine learning models for materials property prediction. This second workshop will be presented by Dr. Ryan Jacobs, who is a research associate in the Materials Science and Engineering Department of the University of Wisconsin-Madison. He uses atomistic modeling, data science, and machine learning, materials informatics methods to understand the structure and properties of materials at the atomic scale in order to discover and design novel material compounds for specific technological applications.
Thanks, Aaron, for that introduction. So in Ben's talk, he introduced a lot of the basics of ML and how to use machine learning to sort of perform each step of a supervised learning process for materials property prediction. And so what I'm going to be doing here is showing you how one can use MAST-ML to effectively automate and streamline a lot of those tasks that Ben showed you in detail during his talk. So there's a lot of content in these tutorials, much more than we'll be able to cover in 1 hour. But what I'm going to do is just show a couple, first a basic tutorial using some toy data on how MAST-ML works, and then I'll pivot into some tutorials on featurization and fitting different models to a materials data set of alloy diffusion barriers that were calculated from density functional theory methods. So just some examples using a real materials data set. So when you open up the tool, you'll see this sort of header with tutorial 1 getting started with MAST-ML. There's a total of 7 tutorials. I'm just going to go over probably 3, maybe 3.5 during this session. And we have sort of a little table of contents here with hyperlinks to each of the tasks. And I'll sort of go through these in detail. So the first stage here is really just importing a number of modules that MAST-ML needs. I'm not going to go into a whole lot of detail, but this basically is things like methods to import data sets, perform featurization, and so forth that we'll use down the line here. So one nice thing about MAST-ML is that it aggregates all of your fits, so those parity plots, data files, and so forth into a well-organized set of folders. And so when we start a MAST-ML session here, we're actually just defining a save path, which I've just named after the tutorial name here. And what this line does is it simply instantiates your MAST-ML session. So when you're in this Jupyter Notebook on NanoHub, you can actually open the folder that contains these tools and information, and everything is going to be saved in these folders here. So as we go, this folder will become populated with a lot of different tests and data and statistics and so forth as we go. So I'll often refer back to that just to show you sort of how these things are organized. There's also examples of images pasted into the tutorial as we go. So for the purposes of this first tutorial, we're just using the toy data set of the Boston housing data. This is a toy regression set that is part of scikit-learn and is often used just to get one's hands dirty with some machine learning basics. We have this scikit-learn datasets module, which allows for easy import of all the scikit-learn datasets. So we're just using the load Boston method to extract the X and Y data, so the features and all their data points, and then Y is the target data of the housing prices. Like Ben showed with the band gap data, these are basically just pandas data frames of organized data. So our X just shows that we have 506 data points with 13 different features. And then if we look at the Y data, these are median house prices in, I believe, tens of thousands of dollars. So as you can tell, they're very out of date, especially for Boston. But we have 506 data points that we're working with here. So typically before fitting machine learning models, one typically will pre-process the data so that it's standardized in some way. Because we have features like house square footage or zone number or so forth, these are different physical objects, much like an atomic number or atomic radius have different units. And so to pre-process things so that they have standard deviation of 1 and mean of 0 sort of removes the unit scaling of these parameters. So we can define a preprocessor object here with the sklearn preprocessor. The nice thing that MAST-ML does is we sort of wrap on top of common modules and classes in scikit-learn so that, for instance, any preprocessing object in scikit-learn can be called by its string name here. And so we sort of envelop the entirety of the scikit-learn functionality into MAST-ML in this way. Similarly, we can define now to these objects, and then we're going to do a fit, the actual machine learning fit in a moment. But here we want to just define a couple of models that we're interested in fitting to these data. And one of the nice things about MAST-ML is that it will evaluate all the permutations you give it. So if you give it 5 models with 3 different feature selectors and 2 different types of data splitting tests, it will do 5 times 3 times 2 splits for you automatically and save everything in these folders. So for the purposes here, I've just defined a very basic linear regression model and a kernel ridge regression model with RBF meaning the radial basis function kernel. So MAST-ML takes a list of models. So this line simply just puts these models into list form. And now we actually will do our first fit. So for the purposes here, we're just going to do a basic random cross-validation exercise similar to what Ben described. And so here, this line simply defines the repeated k-fold cross-validator. And then all of these data splitters are ways to assess the performance of models, right? You could fit to all the data, you could fit to random subsets, and so forth. And all these splitters have this evaluate method. It takes a lot of arguments, but for the purposes here, all we have to do is give it our X data, which is our features, our target data, the models we want to fit to, this MAST-ML instance, which you don't really have to interact with, but it basically just keeps track of all the folders and saving paths and so forth. Our preprocessor, so that it knows to standardize the data before every fit, and then the save path, which is where the data is going to be saved to. We also have a verbosity tag, which controls basically the number of plots for every split that are created. If you feel your runs are going slow, you can reduce this to like 2 or 1, and it'll have less output. So this is currently running, and I have a screenshot here of what the output would look like on my Mac, but I'm going to go to the NanoHub folder in a second here. But basically what happens is for every model and permutation you're running now, I have this linear regression folder and my kernel ridge folder. So what's happened is that the Boston housing data has been evaluated with 5-fold cross-validation using the preprocessor I specified in these 2 different models. So if we go under the kernel ridge model, we have subfolders of every split that was investigated, because there's 5 splits. And then here you'll see that there's just a treasure trove of data files and analysis files for every split. So we sort of have taken a kitchen sink approach of evaluating all the possible metrics that one may care about. And sort of at an aggregate level over all the splits, we save the best model, and we have images such as these parity plots, which you can open in your web browser, but are also shown in the tutorial slide itself. This is a little large on my screen, but what we can see, we have our predicted versus true with our aggregate statistics here. I've just shown the root mean square error of the housing price. So the nice thing about MAST-ML is that we fit these 2 models, but say we want to fit another model. I'll zoom back in again. I realize that's probably small. So if we want to fit a 3rd model, sorry, going back up here, without starting the session over again, we can say I want to define a 3rd model. It's a random forest model, like we saw in the band gap example in the last talk. And we can run our same repeated k-fold cross-validation, this time only on model 3. And you can sort of simply add these in tandem, and it will just make a new folder for you and run the random forest model. So now we see our random forest results have been added here, and it's still running. So you'll see these splits pop up and then all the associated data as the fits are completed. I sort of left my previous results here, in the notebook, but you will probably see if you open your data files that you'll have slightly different fit statistics based on, some of the randomness of how the models are fit. But what I just did here was I was just looking at parity plots of my linear model, got an RMSE of about 5. Kernel ridge was a little bit better, root mean square error of about 4.6. And then my random forest was best with a root mean square error of about 3.7. So this can, allow you to very quickly use different model types to assess their performance on the data that you care about. Here we just use a toy data set, but any tabular data set, of materials property prediction would be suitable. There are other types of analysis that MAST-ML does. These are things that we sort of aggregated over the years of during research projects when we're like, oh, this type of analysis or plot might be useful to show a certain message. And one thing that was sort of interesting was this best worst split plot. So I only performed 5 splits here, but if you perform many splits, you'll just by happenstance, you may split on particularly good sets of data or bad sets of data that yield different fit qualities. So here we've just shown the best split root mean square error in the blue, which is about 2.6. Versus the worst split, which is 4.5. So while before we were looking at sort of average aggregate statistics over cross-validation, it can also be beneficial to see, a best case or worst case model performance. So that's really the conclusion of the first part of the tutorial, where I just show you, using a toy data set, some of the basic functionality of MAST-ML. The second tutorial is actually on some more details of importing data and cleaning it. I'm not actually going to go over this one, but I just want to say briefly, the types of data cleaning that Ben showed in his talk, where you have repeat values or missing values, characteristics of real data that one tends to encounter in the wild. MAST-ML has a number of utilities that can either straightforwardly remove them or impute mean values or values from a specific fit so that you can have sort of smart imputation of missing data. And so there's a number of methods there that will allow you to sort of clean up your data prior to doing fits. So for our purposes here, I'm just going to skip to the third tutorial and sort of assume that we have clean data that's basically ready to go. Okay, so in this third tutorial, we're going to shift gears to working with a real materials data set, which will need featurization prior to fitting with models. And so, here, much like with the structure of the first tutorial, we have a number of imports to start this session. And I'm not going to go over these in detail, but I'll just show sort of how they work as we use them. Here we make a new safe path. So we're sort of in a new section. So I'm going to have a new safe path with tutorial 3. If we go back to our folders, what you should see if you go all the way out is you'll have a separate folder with everything from tutorial 3 saved separately from tutorial 1. If you want to download these and look at the files later, there is a way to do that I can go over at the end. But for now, we're going to be looking at this feature engineering tasks. So typically you'll want to load data that you have stored on your computer. Maybe it's a CSV file or an Excel file. And here we have this sort of local data sets module to handle this. You may ask, like, well, why do I need all of this instead of just pandas read Excel? And the reason is that typically the data that you have contains a lot of extra information that the machine learning model either doesn't need directly or is useful for understanding other aspects of your data. And what I mean by that is, you have your X features and you have your target data, but you also probably have a lot of extra columns that either denote maybe a citation from a paper where you found the data, so like provenance information, that reliability information that Ben showed in his band gap data, or chemical groupings that you might establish. And so this data loader loads a dictionary of your data where you can define the X data, which is all your features, the Y data is your target, And then X extra is all that extra stuff I just described, like citation info or group information. And then the chemical groups are their own sort of separate entity. So if we just look at the X data that we've loaded in, there's actually nothing there. So this data that we have is, we'll look at it, actually, I'm going to add one more cell. I want to look at the extra data. So X is empty, so we have no features, and that's by design. But if we look at the extra data, we have a series of material compositions. And so these data were calculated with DFT, which is an atomistic quantum mechanical method. And so they're metal alloys. So we have these metal hosts. It's like silver here, zirconium near the bottom of our data frame, with these other metal dilute impurities. So silver and silver is just pure silver, but silver cobalt is a metallic silver host with a cobalt impurity. And the target data that we're trying to predict here, if we look at our Y data, these values are DFT calculated migration barriers referenced to their host values. So it's basically the energy barrier for this solute atom to diffuse in its host. So that's the data set that we're working with. So we have no features. And for the purposes of this exercise, we're going to use the same sorts of elemental features that were shown in the previous band gap example. And those were previously generated, and here we're generating them on the fly with this elemental feature generator. So what this does is it just needs information on the material compositions. And so we just give it the column containing the material compositions. And then every material composition will have a number of properties such as atomic radius or electronegativity and so forth that are extracted from a lookup table. But there's various operations that one can do to build an extended feature set. These are things like taking the maximum value in the composition, the minimum value, or the means. And so this set of keywords basically defines the operations on the features to be generated. And like I showed before, every MAST-ML class has this evaluate method, which conducts the generation process and then also ends up saving a folder with your generated features. So we have this generated features Excel file, which was similar to what we saw for the imported for the band gap demo before. So now, previously our X data was empty. If we look at it now, we have a set of 404 feature columns. So things like atomic number averaged, average atomic number difference, et cetera. If we go to the right, we can see all these different types of elemental properties that have been calculated. So we only have 408 data points, but we have 404 columns. So this is likely too many features, and so we are going to down select with feature selection in a moment here. But one thing I want to show before doing that is that you can link feature generators together. So I just went from nothing to having my elemental features, but what if you want to add a different type of features, say by one-hot encoding or some other method? So here I'm just showing a one-hot encoding method where I'm going to encode every alloy class by having a one-hot encoding of the host for the material. So we have these different hosts, so silver, aluminum, gold, et cetera, and we can use this one-hot group generator to basically map these different distinct groups into one-hot vectors. So if we do that, it'll just take a moment. We're feeding in the X data we already had, which was 404 or so features, I think. So now we're up to 419. So if we look at what our X feature data frame looks like now, we still have 408 data points, of course, but now we have 419 columns. So we've added these one-hot encodings of all these group classes. So this is the kind of thing that you can do if you want to continue fleshing out your featurization process. So again, we have way too many features, probably going to have overfitting. And so what we want to do is we want to select sort of the most pertinent set of features. And first to do that, we again need to normalize our data to remove the impact of units. So I'm using the same type of sklearn preprocessor that we had before. And you can either pre-process on the onset before doing any model fitting, or you can pass the preprocessor to the model fits. It's probably more correct to pass it to the model fits, but for our purposes here, I'm going to preprocess at the out. So again, if we call our evaluate method, we'll see this saved. So we had our one-hot group generator data saved, our standard scalar data saved as we go. And what we can see is our X data is now pre-processed, so our scales are totally different here. So each feature column now has essentially mean 0 and standard deviation 1. So I just looked at this column of the arithmetic average for atomic number, and its mean is indeed extremely close to 0. Its standard deviation is exactly 1. So our data is sort of pre-processed in the manner in which we expect. And what I'm going to do here is sort of select the most important set of features to use in our subsequent model fits. So there's a number of ways to do this. I think something that we saw with the band gap example is you can remove highly correlated features, say based on Pearson correlation or some other statistical metric. There's forward selection, where you sort of iteratively select the feature which contributes the greatest information gain, say by reducing an error metric like mean absolute error. Here, I'm choosing to rank features based on their random forest feature importances. The reason I'm doing this is that it's fast, so it's good for illustrative purposes in the tutorial. And it also tends to work quite well, honestly, and it's much faster than, say, forward selection. So this feature selector is called Ensemble Model Feature Selector. It's kind of a mouthful, but basically it uses an ensemble model, like a random forest, to rank the feature importances and then sort them and select the most important features. So there's really only two important inputs here: a model that it needs and the number of features you want to select. Here I'm selecting 20. And the model I'm using is defined like the other models that we used in our previous fits with the Boston housing data. So here I'm just using a random forest regressor model. Only certain types of models will work. So you'll get an error flag if you change this to, say, linear regression. But any of the tree-based models should work. Again, we evaluate it, call this evaluate method like we have for the other methods. And what it's going to return is just, so it's done already. And we can look at our output and we'll see that we have our feature selector output. So we'll have an Excel file of all the feature importances and our list of selected features. But sort of most importantly, it returns the X data of just our normalized and selected feature set. So as you can see now, we're down to 20 columns. As I mentioned before, there are other methods that MAST-ML enables to do this. I'm not going to go through them in detail. There are a couple tasks here, like using a SHAP feature selection approach and forward selection in a little bit here. But one nice visualization to understand, is 20 features enough? Should I select more? Should I select fewer? Is to make a learning curve. And so we have a learning curve routine, again, which just takes the model, the X and the Y data, and some kind of feature selector method. And what it's going to do is it's going to plot an error metric like mean absolute error as a function of the number of features selected to help inform you whether or not you have a sufficient number of features. And the important thing here is to select a number of features such that you have optimal performance, but you don't start overfitting your data. And while this is running, I'll just show the output I had here from before. It actually makes two types of learning curve plots. The first is what I call a data learning curve. So this is mean absolute error versus the number of training points. So this just gives you information about whether expanding your data set may offer you some appreciable gains in your model performance. What we can see here is that early on we get a large gain, and then the gain starts to level out as you'd expect. Now there might be practical limitations to acquiring more data, right? Like you may not be able to run the experiment that uses it, or you don't have enough time to do more simulations. But it can at least just give you an idea about the potential gain of having more data. And then the second, which is what I described before, which is the error versus the number of features. Again, looking at this red data, which is your validation score, this is really what you should be looking at. What we see is we see a large gain large reduction, sorry, of mean absolute error for up to about 10 features. Then once we hit 11 features, it's essentially flat. So I had selected 20 features for the purposes of this exercise, but what this learning curve teaches us is that really stopping at, say, 10 or 11 is probably sufficient. And if we were to keep going, it may stay flat for a while, or the validation score might even start to increase in the case of model overfitting. So I think our learning curve is probably done. Yep. So the learning curve data, like I just showed, is also saved here in the output. And the feature learning curve I got from here even shows, wow. So for this particular model, stopping at 9 or 10 features is probably sufficient. So a little bit different performance from what I had shown before. Okay. I'm not going to discuss forward selection just because it takes a while, but if anyone is interested in running that, it's here in the notebook and you might get a slightly better model performance. Okay. So that sort of concludes tutorial 3 with the feature generation, preprocessing, and selection methods. And what I'm going to move into more is a little bit more of the meat of fitting different types of models and different data splitting tests to assess their performance. Okay, so just moving on to the 4th tutorial here. So we're going to use the same data set, this diffusion data set, materials data set from before, and we're going to fit a number of different models to this data and compare their performance. So as with previous tutorials, we just have some imports and making our new save path. So now tutorial 4 will be in this models and tests folder. We don't have to do the featurization as before, what we could, but I'm just going to load in a pre-made data set where the features have already been generated, just so that we don't have to repeat that exercise. I will say that this particular feature set has 287 features, which sort of motivates us to, again, perform our feature selection to down select to the top 20. I'm actually going to use 10 because I found, it doesn't matter what you use here, but I'm just going to select 10 to make things go a little faster. And also because from our learning curve from before, we saw that our validation score basically leveled out at 10 features. So this is the same cell that we ran in tutorial 3 a little bit above, where we just used this ensemble model feature selector to down select our feature set. One thing I mentioned when we were looking at the toy Boston housing data was the ability of MAST-ML to iterate over many model types and test types. So for our purposes here, I've just selected 5 commonly used scikit-learn models: linear regression, kernel ridge, Gaussian process regressor, random forest, and a basic neural network with a couple of hidden layers as indicated here. So we have 5 different model types. And once again, MAST-ML takes a list of models as input. So this line just puts them all into one list. And as with our previous exercises, we're going to stick with our preprocessor, our standard scalar preprocessor that normalizes all the features to have mean 0 and standard deviation of 1. One thing that I'll just briefly remark on here, but not go into too much detail on, is trying to answer this general question of like how to know when a fit is good. Like, what error is good enough, or what's a benchmark to compare to. So one thing that we've done is develop a few benchmark tests. They're sort of naive tests to compare model performance against. So one example is, does my model do better than just predicting the mean of the data? You'd be surprised that sometimes models don't do much better than predicting the mean, in which case you sort of have a minimal information gain of using a model versus just this sort of dummy model of guessing the mean. Or another test where you essentially permute all of your data, and which should remove any correlation between the features and target and try to predict the data that way. And if you're not doing much better than predicting against a permuted data set, then your model does not contain much useful information. There are others as well, but I'm just going to select the mean and permuted one for now. Previously, we had focused on root mean square error as our metrics. There are a number of metrics available in MAST-ML, essentially all the metrics from scikit-learn plus some custom metrics that we've made. So for our purposes here, I'm just going to use the R squared score, mean absolute error, root mean squared error, and then probably one of the least used but most informative metrics, which is called the reduced RMSE. And so this is the root mean square error divided by the standard deviation of your data set. The reason that's useful is that it's unitless. And so if you have a value of this that's near 1 or greater than 1, then you don't have much predictive ability in your model because your root mean square error is basically on the same scale of your data set standard deviation. It's sort of a similar spirit of am I doing much better than guessing the mean? Is my root mean square error sufficiently small that I'm a low value? Before going into some data splitters, one thing that you can do is just not split your data at all. This is equivalent to just simply fitting on all the data, which is not great for evaluating how extensible your model is. But at the end of the day, when you want your best model, you're going to fit to all your data and then use it to predict on new test data that isn't in your database, right? And so we have this no split routine, which functions just like any other data splitter with an evaluate method. It's just that it will simply fit all of our models on all the data and give our usual performance output. So as before, we pass in our data. There are lists of models, our controlling MAST-ML instance, which again just manages saving all of the files and writing some metadata. We have our preprocessor. Now we have our metrics list, the save path, which just indicates where to put the data, and then a couple other handlers, such as what types of plots to make, and their verbosity, and so forth. You don't really have to change any of this, though you can. There are some other features to add when we get into some more advanced things that we probably won't have time to today. So essentially what's happening, we're running this one cell, but it's going to run all 5 of those models in a no split method. So if we go back out to our saved values here, we have our tutorial 4 models and tests. And what you can see now is there's 1, 2, 3, 4, 5 different folders, and they're sort of named in this, model name, data split name, preprocessor, et cetera. And then they're ended with a time tag. So for instance, I could run that cell again. It would repeat the calculation, but not save over any data because it's going to append a new date time. So for instance, we can just look in our results for our neural network, look at our parity plot of how our neural network does. And since we sort of, it's too large, sorry. Since we specified 4 different fit statistics, those fit statistics are propagated not only to all the plots that are made, but also the output spreadsheets. Okay. Back in. Let's see if yeah, here we go. Okay. So that was just a no split. So one other thing that we can do like before is we can perform cross-validation on all of these models. I'm not actually going to run this for now because it will take a little while. But what we can do is essentially compare the performance based on the ensuing parity plots that we get from this analysis for each model. Your results will probably differ slightly from what I've shown here, but from a previous fit, I've just shown the GPR parity plot showing a very good fit of just 0.09 in the mean absolute error. Again, just to sort of highlight this reduced RMSE value of 0.28, again, much less than 1, indicating we have a model with some significant predictive ability. And you can sort of qualitatively see this based on the spread about the dotted 45-degree line in the parity plot. Kernel Ridge does slightly worse, an absolute error of 0.112. Linear regression, very basic model. We expect it to sort of do poorly, not so great for any of our metrics. Neural network does pretty well, MEE of 0.163. So you get the idea, right? You can quickly evaluate the performance of different models on a particular data set in a particular test. So here I actually found that Gaussian process regression got the lowest root mean square error, and so was the best here. So we got about 15 minutes. Okay, so there's only a couple more things I wanted to show you with regard to different model types and different tests one can perform. One thing that I think is pretty cool that MAST-ML allows you to do is it allows you to build an ensemble of any model type you want. So the reason this can be good, right, is every submodel in an ensemble is fit to a different subset of data. And so by having an average prediction over many submodels, you can have not only a potentially improved prediction, but also you can get an error bar from those, from the distribution of those predictions. So what we saw before with random forests, a random forest is a type of ensemble model. It's an ensemble of decision trees. And here what I've done is actually made an ensemble of neural networks. So MAST-ML has this ensemble model class, and you just give it a base model name. So the MLP regressor is just the scikit-learn neural network. We can specify the number of estimators. 100 is high. I'm just going to run with 10 for purposes of speed. And then any other keyword arguments associated with your model. So this is a set of 10 neural networks in an ensemble, and we can run k-fold cross-validation as we did before. While that's running, just to look at some previous results comparing tests of a single neural network on our data, where we had, let's look at RMSE. RMSE of 0.214 with one network versus an ensemble network where the RMSE dropped to 0.153. So just by using the same model type, but basically ensembling it in this way, allowed us to have a model that was much better on average than a single model. It's sort of analogous to a random forest performing better than an individual decision tree. So I think that is still running. Oh, it's done already. Okay. I had one other example that I'll just highlight, but not explicitly run. Well, I guess I can run it, it's fine. Which is that gradient boosting methods have attracted a lot of attention for solving these types of supervised regression problems. You know, XGBoost tends to win a lot of Kaggle competitions. And so what I've shown here is comparing the performance of the gradient boosting method in scikit-learn with XGBoost or extreme gradient boosting. So extreme gradient boosting, we've sort of folded that model type into this MAST-ML / scikit-learn framework. And so you call it just like any other model type. So this particular test just does a repeated k-fold test again, where we are just running the gradient boosting regressor followed by the extreme gradient boosting. Just to reiterate, all of these results get saved into their respective folders. So like right now I can see the gradient boosting k-fold test is already finished, and my XGBoost test is still being run. So we can just see how these models perform. And actually, I found that they, at least for the purposes of this data set, they're basically invariant. This one, I think from my old test, showed a slight improvement of XGBoost. Oh no, they're actually about the same. Yeah, so 153 for XGBoost, 151 for gradient boosting. So no real difference here, but again, this type of performance evaluation is case dependent. There is one last thing I'll show, and then one later tutorial that I just want to briefly mention for those more interested in some advanced topics on uncertainty quantification. But the last type of model that we sort of enable easy use of is more sophisticated neural networks based on Keras and TensorFlow. Right, so you may be like, I don't want to use the scikit-learn neural network. It's basic. And what we have is a method to wrap the Keras regressor models into this. So this function just describes the same type of neural network, 2 layers, a 20 node and a 10 node network. much like what we use for scikit-learn. You can essentially define a function which returns your Keras model. So if we were to actually say what this is, I don't think it's a scikit-learn model. Oh, I didn't actually call it. That's why. This is what I get for deviating from the tutorial. Yeah. So it's a Keras sequential object, which makes sense. It's just a sequential neural net. But we have this Keras regressor class, which basically makes the Keras network function like a regular scikit-learn network, which allows us to basically treat it like any other model, and for which we can run our usual cross-validation data splitting analysis to compare the performance of these models. Despite having very similar architectures, the scikit-learn neural network actually performs much worse than the Keras one. From my analysis here, we have RMSE of 0.217 versus 0.148. So again, just one more type of analysis that you can do. So throughout this tutorial, I've basically shown a lot of, we've done sort of full fits where we don't split the data up at all, or we've done random k-fold cross-validation where we're randomly leaving out subsets of the data to perform analysis on. But scikit-learn offers a number of different data splitting routines that can target model evaluation in different ways. One of them is to leave out specific groups. So you may recall when we loaded in the data, there was this groups column. And so you can define a set of groups either on your own or based on different chemical classes that offer another way to split up your data. So for instance, you may hold out all the data containing silver, train on everything else, and predict silver. And that's just a different mode of evaluating your model where in practice, maybe you train on all your data and someone comes in with a test data set that's a new element and wants to understand the scale of error they may expect. The scale of error that they're going to get is higher than a random cross-validation routine. It might be closer to this leave-out group type analysis. So we actually did that for this particular set. So for random leave-out, as before, we get pretty low errors of 0.164. But when you do leave-out group, they get substantially larger, like 50% larger. So MAST-ML has parity plots that sort of show all the data like this, but also per group statistics. And all of the per group fit statistics are also categorized. So if you are interested in the root mean square error on just the nickel data or just the silver data, that's all cataloged in CSV files that are available to you. So that's basically the extent of what I wanted to show. I just want to highlight that the remainder of the tutorials are focused on the latter parts of the model development. So for instance, hyperparameter optimization can make a big difference in our model performance, as Ben showed for the bandgap case. So tutorial 5 shows you how to use MAST-ML to optimize models and basically compare model performance between an unoptimized model and an optimized model with kernel ridge regression. And then the sixth tutorial goes over uncertainty quantification. So, what we focused on a lot, I focused a lot on root mean square errors. So just, how good are your predictions? But there's no error bar associated with those predictions. And of course, the model uncertainty is probably just as important as the actual predicted value, right? And so we have pretty in-depth tools about assessing error bars, but also quantifying their behavior. So for instance, there's a number of error plots that plot distributions of residuals and error bars. Sorry, I'm trying to find, for instance, QQ plots where you plot the quantiles of the model residuals versus some normal distribution to look for outliers. We plot the predicted model errors versus the actual model errors and calibrate them so that you can get accurate uncertainty quantification in your models. And then the last part of the tutorial works on or goes over using your models to predict new test data with calibrated error bars as well. So I think I'll stop there. We're about 7 minutes from the hour. I can answer any other questions or discussion topics that we might have.
Thank you so much, Ryan. Yeah, we do have a couple of questions.
Okay.
First one, thank you for this learning opportunity you are offering us. Please, what are the most used models in material science?
Oof. So I can answer that from my perspective of what I have seen when I read papers. So I think the most common ones for, if we're talking about traditional machine learning that isn't deep learning, random forest and Gaussian process regression are probably the most common models. And those are sort of the ones that that I use the most and that I start with because they tend to perform the best. They're also nice in that they're pretty insensitive to hyperparameter optimization, so they're just easier to work with. If you're talking about deep learning models, it's a bit different, but I would say that for materials property prediction, graph-based neural networks have gained a lot of attention because they sort of map the structure of materials directly to some property with a deep learning method. So,
Thank you. The next question is, what models can you recommend to predict the properties of energetic materials? And then it has TNT, RDX, etc.
okay, yeah. So energetic meaning things that explode, not like energy materials. Okay. I don't think it's any different from other materials properties. So I would, again, if you have a supervised learning problem with tabular data, I would suggest random forest and Gaussian process regression. If you have more sophisticated information like molecular structures or things, then I would, and your data set is large, like you have a few thousand entries or more, then I would look into some of these deep learning methods. Either graph-based networks or message passing neural networks could be beneficial.
Thank you for that answer. And the last question I see currently, what can you do to discover materials, or how do you know that you have discovered them?
Yeah, so right, what I described a lot here was sort of just assessing models, but I haven't actually used it to predict anything, at least in this tutorial. So what you would do once you sort of settle on a model type, you would fit to all your data, so you sort of have the most quantitative model fit to all the data you can. Ideally, you would have some sort of calibrated uncertainty so that you have reliable error bars. And then you would predict some space of materials that you're interested in and get a prediction and an uncertainty on those, and then sort them by some figure of merit. So if we just concretely take the band gap example that Ben showed, and we're looking for single junction solar cells, you would sort all your material predictions based on whether they're close to 1.4 EV band gap, maybe plus or minus some bounds, and then look at the materials that you get. Now, regarding whether or not you've discovered something new, I would take the prioritized list, see if it makes any sense. So if you get, or see if it's practical, say. So if you're getting some plutonium alloy, I would, maybe it's a great solar material, but you're not going to be able to make a solar cell out of plutonium, most likely. So there's sort of simple checks like that to do. And then I would also sort of check against known records just basically by Googling or looking at the ICSD to see if something like that has been explored. And then if you have the means to, maybe a DFT calculation to try to verify the prediction. So.
And sort of building off of that, we go through a sort of rudimentary version of what Ryan just described in the lab activity, which I glossed over. But that last section maybe touches on, I think, maybe half of the points that Ryan made there about, how do you sort of get from the predictions to them knowing that you discovered something, and are you going to be rich or not? Yeah, I think those are good points.
How different is the learning time of the models you told us about?
Yeah, so things like linear regression, very fast, right? I mean, it's a matter of seconds or less. Of things that are not deep learning methods, I think one model that sort of scales the worst with, as far as learning time, dataset sizes Gaussian process regression. The reason for that is the core of the computation is a large matrix diagonalization. So it scales badly as you get to large data sets. So while accurate, GPR can often be a lot slower than, say, random forest. Neural networks, it's entirely up to how many parameters you're fitting, right? So if you have a neural network with a few layers, but you have 1,000 nodes in each layer and are thus fitting 1,000,000 parameters, that's going to take, maybe several minutes versus a simple neural network. Maybe it's a few seconds, but it depends on model complexity and data size at the end of the day. But yeah, GPR and deep neural nets are probably the slowest.
All right. Well, I don't see any other questions. So I just want to take a second and say thank you, Ryan and Ben, for taking time out of your busy schedules to come to our workshop and discuss these wonderful tools. And you have a great day.
Thanks for having us. You have a great day
Thanks,
as well.
Aaron.
Thanks.